So keep in mind, I do try to make sure I record every lecture. So I just had today where WebEx decided to completely white screen, and luckily I was able to restart before class started. But just, keep in mind, I do try to make an effort, but there might be some days where technology just doesn't cooperate with that. And I apologize if that does happen, but just kind of gives you a heads up if you're completely reliant on the recordings. One other thing is that we're getting a little bit closer to the first exam. So for all of those that have accommodations, you'll have to do some scheduling ahead of time, try and maximize the use of space.
Are you gonna be available today for office hours so I can ask you some questions?
I should in my office after 2.
Cause I have class at like, I have class at 2:50, so,
Yeah,
and then I have class after that 40, will be available tomorrow then?
yeah. You can always just send me a WebEx and say like, "Are you in your office?" and just stop by.
Yeah, I'm just confused on how you number 7. I'm confused on how you number 7.
Yeah. Yeah, no problem. Yeah, so anytime you can always send an email, a WebEx, whatever. Or if you're happen to be in the building, I'm up on the 7th floor, so you can just walk by and see if I'm in there.
If you're off to the 7th floor, Daisy.
Yes. 7006. So if you get off the elevator, it's to the right.
When is it?
February 23rd, if I recall the date correctly. So a little bit later in February. Yeah, it's in the syllabus. I don't dare open anything else right now because my laptop isn't happy today. But I'm pretty sure it's February 23rd. I can double check that. Okay. So of course I need to, schedule. So let me know ahead of time if you have accommodations, or even if you don't have your accommodations yet, but you're in the process of getting them, then give me a heads up so I know for scheduling purposes how many students I have to shuffle into additional time slots. Right, so that's all kind of the logistical stuff. So today what we're going to be looking at is different properties of convolution. Right, so we introduced the idea of convolution in the discrete time, which gave us that infinite summation. And then we also had the idea of convolution in continuous time, which gives us the convolution integral. And so there are some certain properties of convolution that we can utilize. And so we can exploit these properties when we're actually commuting our convolutions to hopefully make the math a little bit easier. So the first is commutativity. And we've already looked at this idea, which says that you can take a signal, convolve it with another signal, and it's the same as reversing that order. Right, so when we're looking at, say, the convolution integral, it doesn't matter which one we substitute tau, which one we substitute t minus tau. We can pick whichever one we want to, and we'll get the same result. This is true for any x and y. And similarly for discrete time case as well. We also have the idea of linearity, right? This makes sense because we derive this idea of convolution specifically for linear time invariant systems. So it makes sense that the operation that describes our linear systems would adhere to linearity properties. So this tells us that we can take a signal and we can scale it. And if we take that signal and we convolve it with another signal, this is the same as convolving the two original signals and then scaling. And of course, this isn't the only part of linearity. For linearity, we need this case, and we also need that if we take two signals, let's say x1 and x2, and we combine those signals through addition, And then we take this combined signal and we convolve it with another signal. We can actually take and distribute this out. We convolve the one signal, convolve the other signal, and add together those results. And the last one that we have is associativity, which tells us that if we take two signals, let's say y of t and z of t, and we convolve those together, and then we take this resulting signal and we convolve it with another signal that is the same as convolving x and y, and then convolving the result with that third signal. Right, and then you could also use the commutativity property, right? So you could switch the order of some of those in the parentheses as well, or kind of flip-flop these two. Okay. So what's interesting is that these properties also give us some implications when it comes to our series and parallel connections of LTI systems, right? So we looked at series and parallel connections or systems in general, right? So series, we have the output of one system goes into the next system, right? Parallel, we could have an input which is going to multiple systems simultaneously. And so we can always connect our systems in this way, but it turns out that due to these relationships, if our systems are LTI systems, then there's some interesting things that we can do, right? So let's say that we have our first system. So we'll call this sys1, and it's an LTI system. So what that means is we can characterize this system by using the impulse response, right? So I put an impulse into the system, and I get the impulse response h1 of t, so that h1 of t describes system 1. And then I could take another system, do the same thing, apply this impulse signal, and I'm going to get a different impulse response, h2 of t. All right? So now, if I take and I have some input signal, and it goes into a parallel connection. I have sys1 up here, sys2 down here, and then I take these outputs and I add those together to form my y of t, right? So the output to this system, let's call this y1 of t, and the output of this system we'll call y2 of t. Okay. So my y of t is y1 of t plus y2 of t. So y1 is the output of system 1, and we know that because it's an LTI system, that output is described by the convolution. So y1 of t is h1 of t convolved with x of t, and y2 of t is h2 of t convolved with x of t, right? So this is our y2. This is our y1. Okay. And so what we know is when we look back at our properties that we have up here, what we can do is we can rewrite this using this idea of the linearity property as x of t convolved with h1 of t plus h2 of t. So what this means is that this parallel connection of two systems, we can say, is the same as an LTI system, which has an impulse response of h1t plus h2t. All right, so that tells us if we have a parallel connection, we can essentially reduce this block diagram by combining these two into a single system, which has an impulse response, which is the sum of those individual impulse responses. So the other main type of connection that we can have is a series connection. So in a series connection, we have our signal that goes into system 1. The output of that goes into system 2 to give us our overall output, y of t. Right? So let's call this I'll call that y1. So our y of t, based off of this system here, would be the convolution of the impulse response of that system with the input to that system. This y1 of t is the result of the convolution of this system's impulse response with the input to that system. Right? So if I substitute in the y1 of t into here, I get y of t is h2 of t convolved with h1 of t convolved with x of t. And so based on our associativity property, right, we can take, and instead of doing this convolution first, we can actually do this convolution first. So this is the same as h1 convolved with h2, this whole thing convolved with x. Right, so it turns out that this is the same as an LTI system, which has an impulse response h1 convolved with h2. Okay. So that gives us a way that we can reduce whenever we see a block diagram of systems, right? If we have parallel connection, we can linearly combine those individual impulse responses. If we have cascaded or series systems like this, then we have to do a convolution between those impulse responses. Okay, so a big note to make here is that this combining or manipulating this system order is unique to LTI systems. Right? If you have nonlinear systems and you try to do something like this, right, then this would not work for those cases, right? This is due to that special idea of that convolution and the properties associated with that. All right, so let's take an example where we can see this. So commutativity example. Right. So if I take and I have look at discrete time because we've looked at continuous time for a bit here. So let's take I have an input signal x of n. And the first system it goes to is going to produce the output y of n, which is 2xn. Right, so we can look at our system properties and we could show that this is in fact an LTI system. And now I take the output of the system y of n and I feed it into a second system, which gives me the output z of n, which is a first difference of y of n. And again, we could take a look at this and we would see that this is indeed an LTI system. And so if I take my evaluation for y of n and I substitute it in for here, what I would get is z of n is equal to 2xn minus 2x and minus 1. So now for commutativity, it would say that what we could do is we could actually take and swap these two systems. All right, so we take a swapped order. So that we take our x of n, and now this first system that it goes into is going to be this first difference system. So y of n is xn minus x n minus 1. Right, so again, this is an LTI. And now this output is going to get fed into the other system, which scales it by 2. Right, and I do that substitution, right? Substitute y in here, and I do in fact get z of n is 2xn minus 2x n minus 1, right? So LTI systems, it turns out that we can swap the order and we end up getting the same relationship between the overall input-output. Now we take a look at another example. Let's keep our first system the same. All right, so we have y of n is 2xn. Okay, so a nice LTI system. And then, let's say for my second system, I take the input and square it. Right, so we had seen problems like this before, and we found that this is not an LTI system. So when I plug this in, I take and substitute in my y of n into here, I get z of n is 4 x squared n. And so now if I try to do the same thing I did with this cascaded LTI systems, so I take xn, and now my first system, I'm going to square the input. And then I'm going to scale it by 2. So in this case, if I substitute in my y of n, I get z of n is equal to 2x squared n. Right, so just kind of further emphasizing the idea that these kind of relationships that we derive and how we can make these changes with our systems are unique to these LTI systems. Right, if you have something that's not LTI, then these relationships don't hold. So those are your more fundamental properties of convolution. Some other ones that we come across is the idea of the shifting property. And what this tells us is that if we have a time shift in one or both signals of that convolution, is going to result in a time shift of the output. This kind of makes sense because that dovetails into the idea of that time invariant property that we had, right? And convolution is for LTI systems. So this kind of makes sense. What's interesting is that if we take and we have convolution xt, ht gives us y of t, then let's say that I have a time shift of tau 1 of x, and I have a time shift of tau 2 for h, then my output y is going to be time shifted based off of both of the convolution signals time shifts. Another interesting property is the width property. So this can be a good way to test whether or not you've done your convolution correctly, is that if you have your x of t, which has a duration t1, right? So maybe it's something like a pulse signal from 0 to t1, right? So the non-zero duration is t1. And your h of t has duration t2, then your convolution between these two signals is going to have a duration t1 plus t2. So you might be able to kind of visualize that, thinking about the way we do this sort of flip and shift, right? It kind of makes sense that when you do this output, that you're going to get a longer signal. It kind of comes from that smearing of the two signals together. Okay. One that we come across on occasion, convolution of a signal with an impulse. Right, so if I take x of t and I convolve it with an impulse delta of t, then what I'm going to get is my signal x of t. Right, because we kind of think about this in terms of the flip and shift, right? We take our delta t, and as we're shifting it, all we're doing is pulling off the values of x of t. It's 0 everywhere else. And it turns out that we can utilize this shifting property combined with this convolution property to say that if we take a signal and we convolve it with a time-shifted version of that impulse, that is going to give us a time-shifted version of our original signal. And we'll be seeing examples of some of these things later on. Okay. So we have our time shift property. We also have a time reversal property, which says if we have y of t, x of t convolved with h of t, if I flip the two signals, I'm going to get a flipped version of the output. We'll go back to a potentially more useful property, which can also be a good quick check whether you've done your convolution correctly, at least in some cases, is that if I have an even signal and I convolve it with another even signal, then my resulting signal should also be even. Right, so we could take a look at an example here. I have x of t, and let's say that it has a value of 2 between -3 and 3, right? So it's an even signal because we can flip it across this vertical axis and have the same signal. And let's say I want to convolve that with h of t. Let's say this one also has height 2, but it exists between -4 and 4. When you convolve two rectangles, what you're going to end up with is a trapezoid, right? Because as you take this signal, right, we flip and shift it, you're going to have where it's increasing. At some point, if you have complete overlap between the two, you're going to have a constant integral. And then at some point, your integral is going to start decreasing as this signal moves past the other signal. So you're going to get something like in this case, it's going to look something like that. So there is a little bit of a shortcut if you happen to have convolution of two rectangular pulses like this. So a rectangle convolved with a rectangle. You're going to get one of two cases. If the two rectangles are the same length, you're going to end up with a triangle, because what that means is you're going to have no point where you have a constant overlap between the two, right? If these were 3 and 3, then at some point they're going to perfectly overlap, but you're not going to have that extended flat region. Otherwise, you're going to have a trapezoid. Right? So these are good kind of problems to kind of get you started with the idea of convolution. Right? So just formulating up a couple of these and seeing if you can derive with the flip and shift type of method and doing out those integrals if you can get the same result as a shortcut. So if I take my first signal has a height of A and exists between A and B, and I convolve that with another rectangle with height B, that's between C and D. Then the output that you're going to get is you're going to have trapezoid, where this edge is going to be A plus C, this edge B plus D. Right, so we can compare here, right, minus 7, 7, that worked out. And then this distance here, absolute value, D minus C minus B minus A. And the height is going to be AB min of B minus A or D minus C, whichever number happens to be smaller. So it turns out that you do have these special types of signals, right? This type of relationship holds. This is probably, like I said, most useful if you want to get a little bit more practice with doing convolution, at least what the process is you can just randomly generate some rectangles like this, see if you can do the convolution and see if your result kind of matches up with what you expect the result to be. Right, definitely one of those where to really get an idea of convolution, the more practice that you get, the more it's going to hopefully make sense what it is that we're doing, or at least what the procedure is to do so. Right, so even and even, we get an even signal. If we take an odd signal and we convolve it with an even signal, the result is going to be an odd signal. Right, so let's take, for example, if we had an odd signal, which is going to be an impulse of magnitude 2 at minus 3, and minus 2 at 3. Right, so odd symmetry, because we have to do a flip and a flip for those to match up. And if we convolve this with an even signal, right, so take something like a pulse, like so, what you'd end up with, and this one, we could use the other shortcut that we derived, recognizing that what we're doing here is we're convolving a signal with time-shifted impulses. So what's going to happen is that we're going to get time-shifted versions of this original signal. So this one is going to give us the same signal shifted over to minus 3. Right, so what was at 0 is going to be over at minus 3. And we have a scale factor here of 2. This one's going to take this, copy it over to 3, and give it a scale factor of -2. So the result that we're going to get we're going to have at -7, and this is going to actually go to 1. So we have 1 copy. Of height 4. Then we're going to have another copy, which is going to be -1 to 7. Height -4. So my overall signal is going to look like that. And then the last pairing that we could have with convolution, right? Because we could also flip this even, convolved, odd, because we have the commutativity, right? So we don't need another case there. We have even convolved with even. So the other case that we're missing is odd convolved with odd. We're going to get an even signal. So for this one, let's do a little bit more of a proof here. So let's say that we have x of t, and we're going to say that this x of t is an odd signal. So we know that x of t is the same as -x of -t. And we have our other signal, h of t, which is also an odd signal. And what we want to do is we want to show that when we convolve these two odd signals, our output is going to be the same as y of -t, which would indicate that it's an even signal. So we start with our convolution integral, x of t convolved with h of t is the integral x of tau, h of t minus tau, d tau. And so now I want to see, is this the same as y of -t? Right? So what we would do is we would substitute, wherever we have a t in y of t, we would substitute -t. So we have an integral, minus infinity to infinity, x of tau, h minus t minus tau, d tau. Well, since both of these are odd signals, we know that x of tau is the same as -x of -tau. So -x of -tau. And we can pull out the negative sign here. So this is the same as h of minus t plus tau. We have a negative in here. I'm going to take the negative to the other side. And so this is the same as -h of t plus tau, d tau. And my two negative signs here, those cancel out. So I have an integral x of minus tau h t plus tau d tau. And so now I can do a change of variables. Right, because we want to see if it's similar to what we had up here for y of t. So let's take this minus tau and substitute it with a new variable. So then dv minus d tau. So what we get doing this substitution is y of minus t is minus, right? So difference in sign because of v and minus tau, x of v, h of t minus v dv. Use the minus sign to do the flip. And we can see that this is the same thing that we got for y of t. All we did was we used a different dummy variable to do that integral. So for there we did prove using the actual properties of the signals that this was the case. Right? You could do something similar for the other two cases that we looked at as well. Right? And so an example that we can look at here is, let's say my one signal at -1, I have an impulse of height -1, at 1, a pulse of 1. And I'm going to convolve that signal with itself. Right, so convolution of two odd signals. And what we're going to get is an even signal. So let's take a look at this. Actually, kind of writing out the math here and using our time shift and convolution with its impulse properties. So this signal here, we have a minus delta t plus 1. And now if I was to convolve it with this signal here, minus delta t plus 1. Right, so my minus signs cancel out. Convolving with an impulse, I'm going to get a shifted version of the other signal, which happens to also be an impulse. So I get delta of t plus 2. Right, so that would be convolving this signal and this signal. Right, because I can break this up because of the linearity property, right? Because this is a sum of these two signals convolve with the sum of these two signals. So linearity, what I can do is I can convolve each component with each component over here and then combine those results. Yeah.
So the negative cancel out?
Yes. Right, because the idea of the linearity property, these are just scale factors. So we can pull those out of the convolution. So we pull out a -1 and a -1. So it relates to.
Wait, I thought it was 1 minus 1 and you put out the whole minus 1.
Right, because we have. Where did I just write this? Right, so using this relationship, right? So we have a -1 times delta, -1 there, so we can pull those out and multiply them by the convolution. Right? And I can take delta t minus 1 convolves with delta t minus 1, right? So I would be taking this signal and this signal and convolving them together. And I'd have the same kind of relationship where we take the time shift here, shifts the signal that we're convolving with. Right, so this gives us our delta t plus 2. This gives us our delta t minus 2. Okay, so there's that result. And here's this result. And so now for the other two signals, we have a minus delta t plus 1 convolved with delta t minus 1 minus delta t plus 1 convolved with delta t minus 1. Right, so convolving these two plus convolving these two, we get, right, in this case, we have, or we could pull one of these out. So this has -2 delta t plus 1 convolves with delta t minus 1, right? Because these are the same two convolutions, right? We're just adding two of those. And so for this case, when I add together the time shifts, right, the +1 and the -1 cancel out, and that's where I get my delta t and that height of -2. Right, so you could actually compute out the integrals in this case if you wanted to and verify, but because of the properties that we have, we can take some shortcuts and do this type of convolution more quickly. So more properties, right? I know it's a lot, but being able to recognize some of these can help with our computations. So another property is the derivative property. So if I take and I want to do the derivative of the convolution of two signals, it turns out what I could do is take the derivative of one of the signals and convolve it with the other. Yeah, so potentially useful if you have maybe something that's a, maybe you have a step signal, right? Because once you take the derivative, then it's an impulse, and a little bit easier to do that convolution. And so some potential applications there. All right, so let's take a look at an example where utilizing some of these properties that we've talked about could be particularly useful. Right, so let's say I have a signal A of t, and this signal is a rectangular pulse from 0 to 1. And I want to convolve this signal with another signal which has a magnitude of 1 from 0 to 1, a magnitude of 2 from 1 to 2, magnitude of 1, 2 to 3, and a 0 otherwise. And I want to figure out what is that output C of t. Right? So we could do this using our integral method, right? So you'd have to keep track of all of the different boundaries, right? Because you're going to have a certain region here, and then you're going to have some point you have a split up of these two. So you have 1, 2, 3, 4, maybe like 6, 7 boundaries that you're dealing with, right? So that could be a little bit messy, but we can actually recognize some interesting things here. So let's say that we write B of t in terms of A of t. Okay. So my B of t is equal to, well, we can almost think of this as 3 different regions here, right? So this first region looks exactly like our A of t. This second region, right, it has the same width as A of t. We've just shifted it to the right by 1. And we've scaled the magnitude up to 2. In this third region, right, the width is the same as A of t. The height is the same as A of t, but we've shifted it to the right by 2. Okay. So what's interesting here is that by rewriting this, we recognize that our B of t is a linear combination of shifted versions of A of t. What we could do is we can take and compute A of t convolved with A of t, which, let's say that's result is M of t. And then we can use our time shift property. Okay. So instead of having all of these different regions, we can take and do one simpler convolution and then utilize our properties to figure out this more complex convolution. Right? So if we take and convolve A of t with itself, we're going to get M of t is going to be a triangle of height 1, width 2. Right, so you could either use the kind of the shortcut of convolving 2 rectangles, or you could do that manually if you want some practice to verify that this is the result that you get when you convolve this A of t with itself. And so then our C of t, which is A of t convolved with B of t, is the same as A of t convolved with A of t plus 2a t minus 1 plus a t minus 2, right? And so now we can use that kind of distributive property to get A of t convolved with A of t plus 2 A of t convolved with a t minus 1 plus A of t convolved with a t minus 2. So all we've done here is just distribute out this convolution operation. And so now we can see that A convolved with A, we already found what that result is. So this is M of t. Here we have the same A convolved with A, but one of the signals has a time shift in it. So we can utilize our time shift property and recognize that this is going to be the same output, but it's going to take on the time shift that was in the signals that were convolved. Similarly here, we have the two A of t's, but with a time shift. So now, to compute my C of t, I can recognize that I have for the first part, my M of t going to look the same as this. We have 1 to 2. We're going to have an M of t, which is shifted to the right by 2. And we're going to have another signal where we shift to the right by 1. And we're going to have a scale factor of 2. Right? And then you can add those together to get a C of t. Something like that. Right, so potentially a little bit easier than doing the convolution directly of these two signals, right? Might be debatable, right? Some might prefer, just going straight to the integral and brute forcing it, but it is an option that we can utilize those properties and say, well, I'm going to do this simple convolution and then utilize those properties and combine them together instead of having to do the more complex integral. Right, so completely up to you what methods you're most comfortable with, but this gives you different options as to how you could approach a problem. All right, so going to go over a couple more properties of systems. Right, so a little bit of a break from the convolution properties. Instead, we're going to back to system properties. All right, so there's also this idea of having systems which are memoryless, right? So we consider a system to be memoryless if and only if h of t is some potentially scaled version of the impulse signal. Or if it was discrete time, right, same kind of idea, h of n alpha delta n, right? So what this means is that memoryless systems output is going to depend only on your present inputs. All right, so that's why we consider it to be a memoryless system, because it doesn't depend on anything that happened in the past, and it also doesn't depend on anything in the future. yeah, in the future, right? So it has no memory associated with it. So we can see where this comes into play. If we take a look at our convolution definition, so a bit of a reminder, our convolution sum, which we could also write in the reverse order, hk x n minus k. Right, so I could actually break up this summation here into the summation of the negative k's our k equals 0 and our positive k's. Right? So in this case, where k is a negative number, so we get x of n plus a positive number, this is going to be dependent on future inputs. This would be our current input. And then we'd have our past inputs, right? So that makes sense then, that to be memoryless, which means we can't have any future or past inputs, we need h of n equals 0 for n greater than or equal to 1 and n less than or equal to minus 1. Or in other words, h of n is just the impulse. And so this relates to a similar related property, and one that we've actually talked about before, but now we can see specifically how it relates to this idea of the impulse response, and that's the idea of causality, right? So we said for a causal system, an output depends on current and past inputs only. Right, and so we kind of just left it as that, because that's a general system definition. But when we're looking specifically at LTI systems, since we know that LTI systems are described by their impulse responses, and we can derive this type of relationship here, right? We also have something similar for continuous time, where instead we would break up the integral instead of breaking up the summation. And so what this tells us is that if my system is causal, then it cannot depend on any future inputs, which means any time that I have future input, this h needs to be 0, and this is going to be true for any negative time. So what this means specifically for LTI is that h of t equals 0 for t less than 0, or hn equals 0 for n less than 0, right? So if you have a impulse response which satisfies this case, then you can also conclude that your system is not only an LTI, but is also a causal system as well. Right? And so we also have the idea of stability. right? So we can consider an LTI system to be bibo stable. Bibo means if we have a bounded input, then we have a bounded output, right? So if your input doesn't go to plus minus infinity, then your output should not go to plus minus infinity. And it turns out that for this case, if the summation of the absolute value of hn for discrete time, or for continuous time, the integral of the absolute value of h of t is bounded, then this is sufficient for bibo stability. Right? So it's a sufficient condition, maybe not a necessary condition for certain systems, but if you have an impulse response which is bounded in this way, then your overall system is going to be bibo stable. So and here, right? So the inverse system, we've also talked about this before. So for this case, the inverse of an LTI system is going to satisfy Hn convolved with H inverse of n gives you delta n, right? Because if you take your delta input into your LTI system, that's going to give you H of n. This is saying essentially if you take that output and then you put it back through this Hn inverse, that you should get back your original impulse that you put in, right? Same kind of idea with Ht convolved with H inverse t should give you delta t. Or if we draw this out, so xn, hn, if we cascade that with the inverse system, then we should be able to get our original signal back. And it turns out if we take these two and combine them based on this relationship, right, this is essentially telling us that what we're doing is just convolving with an impulse signal to get back our original signal. I think we'll have just enough time here. All right. So one other thing that we want to take a look at, and we've already kind of looked at this result before, but we'll reiterate because this is a pretty interesting result, is that of the step response. Right, so with a step response, we take our step signal, u of t, go through our LTI system with impulse response h of t. And since this is a special kind of output, we'll call this y step of t. And so what we found before, we took a look at this and we said, well, y step of t is the integral u of tau, h of t minus tau, d tau. is the same as integral 0 to infinity h of t minus tau d tau. And I can do a change of variable with v equals t minus tau. All right, so trick that we've used quite a bit in this class so far already, right? Just basically relabeling things so they look to be in more familiar forms to what we're looking for. And what we get doing that change of variables h of v dv, right, which tells us that our step response is the integral of our impulse response. Right, so step response is the integral of the impulse response, or our impulse response is the derivative of our step response. Right? And so what this means is that we can take, and we can also figure out, say for some system, we want to figure out the impulse response. Sometimes it's actually easier to calculate the step response first and then take the derivative. Right? One thing that I don't think I noted last time for the discrete time case, what this means is that your y step, if you plug this in, right, you're going to have a summation. So instead of it being an integral, it's more of an accumulation that describes that step response, which means that when you want your impulse response, you're going to take a first order difference, right? So it turns out that there is a relationship if you do it in discrete time as well, or if it turns out that doing this step response first is easier, you can compute the impulse response, and vice versa. If you already have the impulse response, you don't have to re-go through the derivation. You can do this cumulative sum to get to your step response. Right. So I already kind of looked at this example, but give you another interesting little trick here. So RC circuit, we want h of t from our step response. Right, so seen this circuit a couple times now. We have our input x of t voltage. We have just a simple RC with our output voltage across the capacitor. And what we get is x of t is y of t plus dy of t dt. And we're assuming zero initial condition. Right? So if x of t equals u of t, then our output is y step of t right? So you can do the solving the ODE here. Well, it's actually interesting trick that you could utilize in this case is that you could actually multiply both sides by e to the t, right? So if I do et y step t plus et dy step dt equals e of t. Right, so we don't want to forget that we do have a u of t here, but we're just going to ignore that just for now and only look at the case where we have one on the other side. Okay. So what's interesting about this is that I can rewrite this as d dt et right? Because if I apply the product rule there, I would get derivative of e of t is et times the second plus the first times the derivative of the second. So what this means is that by rewriting it this way, I can integrate both sides. I integrate away the d dt, gives me the integral of e of t. Right, so that indefinite integral would give me e t plus some constant c. And then I utilize my initial condition to figure out what that constant c is. So the initial condition is 0 when t is 0, which gives us c is minus 1. So what I get et y step of t is e to t minus 1. I can divide through my et, recalling that we did have a u of t before that we temporarily set to the side. So my actual result is y step t 1 minus e to the minus t u of t. And so then my h of t is the derivative of this, which when I take that derivative, I can multiply this out, minus e to minus t, u of t, right? So we're going to have some impulses and things that cancel out, and eventually we get e to the minus t, u of t, right? So it turns out that for this case, we could actually get our impulse response without actually solving an ODE and then just doing a simple derivative at the end, right? And all we had for integration was an integral of an exponential, right? So an interesting little trick, another way to get at it, that you can actually avoid ODEs in some cases. So just kind of an interesting thing, right? But then once you have this, then you can figure out, right, we know what the impulse response is for the circuit. So for any other signal that we put in, we can compute what that result would be. All right, so I think I'm right about at time, so we'll stop there.